Welcome back to Math 432, Applied Combinatorics. I'm Professor Asaph. Today we're going to be talking about how to count things in two ways. So a formula is really just a way of counting. And so an equation or an identity is two ways of counting. What we're going to count for this example is how many dots there are in an n plus 1 by n plus 1 grid. So here's our example where we have n equals 4. So, of course, n plus 1 equals 5. So here's our 5 by 5 grid. And we want to just count how many dots there are. So the first way that we're going to do this is by counting the area. So the area is just sort of the general way that we know how to do this. Well, there's going to be count by area. And so we're going to get n plus 1 squared dots. That's the discrete area of the region that we have in here. So it's pretty straightforward. Where things get interesting is when we count in a less straightforward way. So let's copy this and move it over to here. And maybe we'll change the color too, just so that we can differentiate our two methods. So our second method of how we count is going to be by diagonals. That's another perfectly reasonable way to count. So we have one thing here on the diagonal. This diagonal gives us two things. This diagonal here gives us 3. This diagonal gives us 4. Here we have this long diagonal that gives us 5, and now we're going to count down again. So we're going to get 4, 3, 2, and 1. So it's a little more complicated to write down what we have here, but it's interesting in that it's going to give us a different answer. So here we have the long diagonal. So this, maybe I'll call this the middle diagonal. And we see the top region and the bottom region are the same. So we're going to get a 2. And then what are they? Well, they're just the increasing strings of numbers all the way up to n. So this is for the top and the bottom. And this is increasing diagonals. So what does that give us? When we put it all together, we get a nice identity, which is that n plus 1 squared, the number of dots, is equal to the number of dots. No matter how you count it, the number of dots is the same. So we get this identity. And this is actually a familiar identity. So let's massage it a little bit. Let's solve it for this quantity. And then hopefully it'll look a little more familiar. So we get n plus 1 squared minus n plus 1 is equal to twice the sum of the numbers 1 up to n. And of course we can factor in n plus 1 out of this, so let's do that. N plus 1, we have n plus 1 minus 1 is equal to twice the sum of consecutive numbers. And then, of course, we can simplify and divide by 2. And we get the formula that we deduced last time by induction. And this gives us a really nice, maybe more combinatorial proof of this identity. It's a concrete proof of this identity. So somehow it's better in that way. It gives us a more intuitive notion. And I'm going to let you guys know these are called the triangle numbers. And of course, we can see why here, when we're counting these up, this is our triangle. So this is a way to graphically think about numbers. Of course, there are different types of numbers that we could do. These are the triangle numbers. The square numbers, you know, and we get those just by drawing a square. And there are pentagonal numbers, hexagonal numbers, and so on and so forth. But whenever you have these sort of geometrically named numbers, then you should suspect that there's going to be some kind of counting dots proof that is line hidden inside. So we'll do a couple more examples of how to count things in two ways. And keep in mind that whenever we do these proofs, there are different ways to prove things. I think this proof is very elegant, but you could also prove the same identity, the top level identity that we have here, or of course, this identity by induction. That's a perfectly good way to do it as well.